Say good afternoon, participants. Once again, we have been successfully going for the session 3 of the day 3. So good afternoon, sir. Dr. Utsap Kundu, sir. Good afternoon, sir.
Good afternoon.
Yes,
Very
sir.
good afternoon.
So today we are going to have the session 3 from Dr. Utsap Kundu. Sir, just before handing the session to Dr. Utsap, sir, I want to brief about the sir profile to all of you, and so we can have the session. And sir is going to take about the today very interesting topic that wireless EV charging, where the application of power electronics converter is going to be have. Sir is going to share his knowledge pertaining to this subject. And sir is received his graduation in electrical engineering from the Indian Institute of Engineering Science and Technology from Aura, India in the year 2010. And sir also did his master degree in machine drives and power electronics from IIT Kharagpur in the year 2012. And sir also pursued his PhD degree in the power electronics domain from IIT Kanpur in the year 2019. And coming to his PhD, during his PhD work, sir has worked on different aspects on resonant power conversion system from the year 2018 to 2021. Almost we can say 3 years of experience in this power conversion equipments, and where he have been this thing, and he has been worked as a staff power system engineer at Max Linear Technologies, which has been located in Bangalore in India, where he has been involved in designing the power management ICs for server application, and is currently an Inspire faculty with the Department of Electrical Engineering, representing the IIC Bangalore, India. His current research interest includes the application of resonant converters, power management ICs, and control techniques in the power electronics. So with this short introduction, I was welcoming the Dr. Utsap sir to share his valuable knowledge and to share the application of power electronics resonant converter, where it can be used for EV charging. And since almost we have been going to be at the end of the third day of the session 3, so almost we have been spent some time on understanding the mechanism and architecture of electrical vehicle, as well as we have been spent some time on understanding the battery management system, thermal management system, and we have been seeing that today morning we have been seeing about the motor control system, motor applications in EV application. Now we'll spend some time on understanding that how the resonant power converter application can be applied for our EV charging application. So without taking further time, I was handing over the session to Dr. Utsap sir. So over to you, sir.
Thank you, Mr. Muthukumaran, for very nice introduction. So I'll share my screen and I'll keep my video off so that you can concentrate on the presentation itself. And
Yes.
the second thing is, if there is some bandwidth issue in the internet connectivity, or if my voice stops coming over to you, please give me a phone call, okay? Mr. Muthukumaran, please help
Well,
me with a phone
yes,
call.
sir. Yes, sir. Yes, sir.
Okay, so is my screen visible?
Yes, sir. We are able to see you, sir. Yes, sir.
Okay, 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 thank you.
The other
So,
participants also
today,
can you confirm it, sir, whether you can able to see the screen?
Yes, sir.
Participants.
Fine, fine.
Yes, sir.
Okay, sir. Thank you, sir.
oh, thank you, thank you. So, we will be mostly talking about wireless EV charging. So, as Mr. Muthukumaran is mentioning that in this faculty development program, already different aspects of EV charging has been talked about. So he named the battery charging system and motor control. So those are very much intrinsic topics to the EV charging and operation of EV, right? So this wireless charging is a bit, I'd say, newer direction where people don't want to use wired connection for charging the battery of the electric. So we'll try to understand how that can happen. So another bigger picture is resonant mode power conversion. This is a we can say a special class of power electronic converters, which is resonant converter. So we'll specifically look at how this converter can be applied to wireless EV charging. Okay. And secondly, uh, we'll actually go into the details of a particular problem of this resonant converter. So let us say we understand that we can use resonant converter for wireless EV charging, but then we have to also understand what is the uh, main drawback of this type of converter, or when we are trying to use it for wireless charging, what kind of problem we can face, and also we'll discuss about a possible solution to that problem. So I'll start the presentation by giving overview of resonant converter so that uh, we can bring the whole audience into the same page. So for the people who have already worked on or have studied resonant converter, the initial part of the presentation would seem to them as trivial, but for the people who have not worked on it, so for them this will be new. Okay, and also for people who have already worked on it, it will be a very good brush up to understand the basics of resonant converter once. Okay, so before getting into that, first let us understand what we are actually doing in power electronics research or in the application area, both in industry and academia. So if we think about a general power electronic converter, we know that we can make the DC power, convert that into another DC level, which is known as DC-DC converter, or we can take AC, convert it into DC, so basically that's the rectifier, or we can take DC, convert it into AC, that's the inverter application, and also we have some cycloconverter or matrix converter that we directly transform AC to AC. So whatever be the case, we will ultimately use inside this black box some semiconductor switches, either MOSFET or IGBT, maybe some diodes, and passive elements, inductors and capacitors. So the common trend is in this sort of power electronics research is to increase the switching frequency at the frequency at which this switch is operated, so that we can basically reduce the size of the passive element. So it's a very common and well-known trend, and people are working in this direction both in industry and academia. So ultimate goal is to reduce the size of this black box. Now, what is the problem? The problem is uh, when we actually switch this converter, and if we try to see the switching characteristic, how it operates, if we think of how a switch is turned on, and if we try to see the current through the switch and voltage across the switch during the turn on process, we'll see that there is some sort of overlap. That means when the voltage is coming down, at the same time, the current is also rising. So this overlap will actually cause some energy loss, because in this duration, we can see both voltage and current are present. Right? So this energy loss multiplied by the switching frequency will ultimately give us the switching power loss. Right? Similar phenomena happens when a switch is turned off. That time the current through the switch comes down to zero, but when this transition is happening, at the same time the voltage across the switch starts rising. So again we see another overlap. So basically, in this general converter, whenever we turn on turn off the switch, we will experience this kind of energy loss in every transition. Right? And the more the switching frequency, that means we will have that many transitions. So in a way, by increasing switching frequency, though we are able to reduce the size of the passive element, we are actually compromising in terms of converter efficiency, because the loss will increase and that will cause the efficiency to degrade. There is another catch. When the converter, we say converter efficiency is degrading, that means there is this loss of energy which will ultimately convert into heat energy, right? So that heat dissipation, so this electrical energy will be transformed into heat energy. That's the phenomena of this loss quantity. Right? So now we have to dissipate that heat. So for that, these semiconductor switches and diodes, these have to have heat sinks so that we can dissipate the heat. So you can see, though we are actually reducing the size of the passive element, but it may turn out to be that the overall converter size is actually either remaining same, or in some designs it may actually increase because of switching frequency increase due to the use of or the requirement of large heat sink which we have to place, uh, which we have to use for mounting this device, semiconductor. So there is a concern of this approach, right? So to address this issue, so what should be our wish list? Our wish list should be, we should be able to increase switching frequency so that the size reduces, but that should not cause the loss to increase. So for that, we need to have some special techniques. So these techniques are called zero voltage switching or zero current switching, right? So in zero voltage switching, so zero voltage switching turn on, what actually happens is, by some means, we actually bring down the voltage to zero before the current starts rising. Okay, so you can see here, by some means, if we can get a switching behavior like this, then there is no overlap between voltage and current. So we can assume, or if we calculate the energy loss in this transition duration, we will see that energy loss is zero. A similar thing can be achieved during turn off, which is called zero current switching, when current is brought down to zero before the voltage starts rising. Again, we do not have any overlap between current and voltage. Right? So now we can see, since there is no overlap and no energy loss during the transition, even if I increase switching frequency, that will not cause the switching loss to go up because there is no switching loss ideally. So that means, if we can ensure this sort of a phenomenon in the power electronic converter, then we can actually increase the switching frequency, reduce the size of the passive element, but we can maintain a very good efficiency of the converter as well. So that being an inherent property of resonant converter, we'll shortly see how resonant converter achieve this kind of. That's why this resonant converter is popular and it is gaining attention for many different applications. So we'll talk about one particular in today. So what is a resonant converter? So what is basically done in resonant converter? So here, what we do, we actually transform the DC voltage to another DC voltage. We have a DC source and we also have a DC load. So this is the basic powertrain of this converter. What it does, firstly, it uses a switch network. It can be a full bridge switch network or a half bridge switch network, and makes the voltage at this node, the VT, a high frequency AC voltage. So you can think of that when this voltage, DC voltage, is switched at a frequency Fs, let us say, then this uh, output voltage of this node, or at the output of the switch network, you will see a high frequency AC voltage. Okay. So that high frequency AC voltage is then fed to a tank network. Okay, so this tank network can be made of some passive elements, some combination of LC. So that will actually create another AC signal, which is VP. Since we have a high frequency AC signal, we can understand, depending on the requirement, we can either buck or boost, or either you can step up or step down this voltage level using a high frequency transformer. So since the voltage itself is at high frequency, the size of the transformer is also expected to be small. But we have to reach to DC. We are still at AC. So here, when we have this AC signal, to make it DC, we have to have a diode rectifier. Then we have a rectified sine wave kind of a waveform after this diode rectifier, where you will have a DC component and you will have higher order harmonics. So we need another filter, either second order LC filter or a capacitor. That decision depends on what kind of a resonant tank we are actually using. Okay, so then we filter out those high frequency components using this filter network, and then we actually get the desired DC voltage here at this port. So we can see in the secondary side we have a diode rectifier, we have a filter network, and we have this load RL. So we'll shortly see how to model this whole thing as a equivalent resistance R, which we can directly assume to be connected across this tank network, right? So for analyzing this sort of circuits, for easy analyzing, what we can do, we can think of this AC voltage VT is applied to the tank network, and the tank network is directly terminated to a equivalent resistance R, which can be defined or expressed in terms of the actual load resistance RL. Okay, so this is one point in resonant converters analysis. Another point to note is that this VT can be a square wave or a quasi square wave, depending on how this switch network is switched. So, due to half wave symmetry of this kind of a waveform, in this VT waveform, if we do Fourier analysis, we'll see we'll have a fundamental component, which is the switching frequency component, and we'll have odd harmonic, third harmonic, fifth harmonic, and so on, right? And this tank, actually, the response of the tank is such that it is capable of extracting only the fundamental component out of this uh, complete harmonic spectrum. Okay, so the current IS, what we actually see in this kind of converters is basically predominantly that has fundamental component, that is the switching frequency. This is a typical harmonic spectrum of any resonant. Okay, so just moving on, keeping this circuit in mind, so the whole big circuit we can actually model as a AC source, tank network, and a equivalent resistance R. So since in the tank network we have some LC component, right? So with that LC component and the resistance R, the whole tank with the load can now also be modeled as an impedance, right? So what we are saying here, we are saying this some combination of LC along with this R. If we derive the transfer function, we can actually express it as an impedance Z, right? And here we are elaborating this switch network. Here we are showing it as a full bridge network. Okay, so this is a full bridge switch network which is switching this DC voltage, and an equivalent impedance is connected at this switch node. Okay, and we can identify from our previous circuit that this is our AC waveform which we are talking about, VT, and this is our current waveform IS going into the impedance. Okay. Now this switching of this full bridge network, we are assuming that, let's say, we are doing full square wave switch. That means we are not doing overlap between M1 and M3. So we are not generating a quasi square wave. Rather, we are generating a full square wave at the across the impedance Z. Okay. Now let us say if the impedance Z is such that it is actually presenting an inductive nature, right? So that LC design we have made such that this impedance is basically an inductive impedance. So what will happen? The current which is flowing through this impedance will basically lag this excitation voltage V, because that's normal AC circuit, right? If we connect the inductive impedance across the AC source, the current which will flow, that will definitely lag that AC voltage. Right? Now, if we can see that this current, since it is now lagging, so we try to understand what happens before we turn on, let's say, this switch M1. So before turning on the switch M1, you can see that the current is actually negative. That means the direction shown here, and the actual direction of current during that instant shown here, so that is being negative, the diode D1 will actually conduct before the switch M1 is turned on. Okay. So here what will happen when we will turn on the switch M1 and the switch will actually start taking the current. Before that, since the diode D1 is already conducting, then the voltage across this switch was approximately zero if we neglect the diode drop, which is, let's say, 0.7 volt or 0.6 volt. So when the switch current will start rising, at that time already the voltage across the switch will be zero. So that means this transition will be a ZVS turn on transition, and it will not cause any significant switching. Similarly, we can analyze every other transition and we will see every time before the switch turns on, its antiparallel diode is already on. So all these turn on transitions are basically ZVS turn on, and any turn on transition will not cause switching loss when we can ensure a lagging impedance. Okay. Similarly, we can analyze if this circuit is capacitive or if this impedance is capacitive, then the current IS will be leading the voltage VT, right? So if it is leading, then we'll see that before turning off of the switch M1, the current direction being uh, negative again in this case before turning off, then the diode D1 will conduct, and ideally there will be no current to this switch. Okay. So when we actually turn off the switch, that means the voltage transition will happen, right? So turn off means the voltage will rise from 0 to the blocking voltage. But before that, the current has already become 0 to this device, right? So that will again be a soft turn off transition, which we call zero current switching turn off. So if we can ensure this, then all the turn off transitions, what we'll see, we'll actually see that to be zero. Turn off transition losses. So that means in this case, the turn off loss will be zero, and we can still expect that the efficiency of the converter will increase. Okay. Now people have seen if we compare between these ZVS and ZCS operation, you can understand that for this ZVS operation, turn off of every switch will still have loss. Okay, and similarly for ZCS operation, turn on of every switch will still experience loss. So it has been seen that due to the reverse recovery of these diodes, the turn on loss is actually more. So this impedance, so it is more intuitive or more natural to keep it as a lagging impedance rather than a leading impedance in typical resonant converter design, so that to achieve ZVS turn on instead of ZCS turn off operation. So it has been seen that the first operation gives a little better efficiency or a little better, little less switching loss in when we ensure a inductive impedance. Okay, so this is the basic ZV. This is how the resonant converter can achieve soft switch. Now we'll come to the point which we left here quickly, that we said that this R can be related to the actual load resistance Rn. So if we analyze the secondary side circuit, in the secondary side we have this rectifier, diode rectifier, let's say with an LC filter. Okay, so in that case, if we try to analyze, and if we assume that this current IL is ripple free, that means the inductor is so large that this current IL can be assumed to be almost constant. And then if we apply charge balance across this capacitor, we'll understand that the average current through this inductor is basically equal to the load current IDC. Okay? So this is a similar thing which happens in our normal buck converter. So we apply charge balance at the output capacitor, and we see that the current through the inductor, average current through the inductor, is actually equal to the load current. Okay? So if we do that, then if we try to draw the current waveform Ix, we'll see that Ix is basically a square wave, right? Because this current is a constant IDC current and this diode rectifier is operated, right? So that will make this current a pure square wave. Now we see what is the voltage Vx from the other side. So this node being current strip, since we have connected an inductor here, so naturally we need a AC kind of a voltage source here to be excited by an AC voltage source, which actually this job is done by our resonant tank. So resonant tank takes that square wave VT waveform. If we go back and recollect, it takes the square wave VT waveform. Then we have this resonant tank, and then the VP waveform, what we are seeing here, that will become a approximately sinusoidal voltage, right? So that is shown here as this Vx1. So this is basically the fundamental component of that voltage. Now using this, we calculate the fundamental component of the square wave current, which is 4 IDC by 5, right? If you do Fourier analysis of this square wave, and the voltage, since this voltage is VDC, and if we try to calculate the fundamental component of our AC voltage here, we will see that this is actually related by our known equation of diode rectifier, which is 2 Vm by pi, or 2 into peak of this voltage by pi. Now the resistance, equivalent resistance seen from here, if we calculate, definitely we will have a transformer turns ratio factor coming, which is 1 by n square, and this there will be this ratio of two fundamental components, fundamental voltage and fundamental current. So this ultimately turns out to be the relationship between the equivalent resistance R with the actual load resistance RL to be multiplied by this factor pi square by 8 divided by n square. Okay, so this is the case when we have inductive filter or LC kind of a filter. Next, if we have a capacitive filter, let us say at the output node, and that time since this side of the uh, switching network is a voltage strip one, then we can think of a tank which is actually feeding a current to this node, right? So this is just opposite to what we saw in the previous architecture. So in this particular case, what will happen? Now, this voltage we can assume it to be repeated. Then this voltage will actually become a square wave, right? Because this is a DC voltage and the rectifier is operating, and a current source or a AC current source is feeding from this side. So the current now we can assume it to be close to sinusoidal, or we can consider the fundamental component of it. And the voltage is actually a square wave. We can again take the fundamental component of that square wave voltage, and then we can similarly calculate as previous the peak of the voltage this time and a relationship between the DC current and the peak of this current, right? And again, if we do the same manipulation, this time we will figure out that the factor has changed from previously pi square by 8 to 8 by pi. Of course, the 1 by n square, the transformer trans ratio factor will remain the same. So this is the basically modification when we use a capacitive filter. Okay, so we go back to the powertrain from where we started. So first we studied the primary side part, assuming a resistance is getting reflected, and we tried to understand how the stock switching can happen depending on the nature of this tank. Okay, then what we did, we tried to understand how this resistance R can be related to the actual load resistance RL. That means we actually analyzed the secondary side of this converter. Okay. Now, what we have not yet analyzed in specific, what can be this tank network? What are the possibilities in the tank network, right? So, if we go a little further and we take the very basic tank network, which is uh, probably first invented for this resonant converter application, that is series resonant converter, right? So in series resonant converter, actually the tank is comprising of two elements, one capacitance C and one inductance Ls, and they are connected actually in series. Okay, and this R is basically the equivalent load resistance which we actually reflected in primary. So it is sufficient to analyze this circuit or nature of this circuit to understand how the whole converter will behave. So for that, the first thing is for any tank network or wherever we see resonance, we try to understand what is the resonance frequency. So here it is very easy to understand because only two components we have. So naturally, it's natural resonance 1 by square root of LSC. Okay. And next, what we do, we try to understand what is the impedance looking from this node. So which is this node where our full bridge switch network was connected. So this is basically we are trying to understand what kind of what is the nature of the impedance that our full bridge switch network will be looking at, right? So here if we see that if this resistance is shorted, that is the short circuit impedance, that if we plot, we will see this is basically inductive in nature when the excitation frequency, or basically that is the switching frequency of our full bridge network, that is greater than the resonant frequency. So that time it presents a inductive kind of a impedance. And if it is lower than the resonant frequency, the excitation, then it actually presents a capacitive kind of an impedance. Okay. So from this itself, we can easily understand that we switch the full bridge network at a frequency higher than the resonant frequency, then we are going to achieve zero voltage. And if we do the other way around, if we switch it at a lower frequency than this resonant frequency, then we will get a zero current switching. So this is basically the short circuit impedance characteristic. And the open circuit impedance we can understand if we open this resistance. There, this will actually become close to infinity because it's completely open circuit. The whole tank becomes open. So that is another nature of this resistor. And interestingly, for any power converter, if we are operating at a rated load after designing the converter, we already know the power rating of the converter, we are operating close to the rated power condition or rated load condition, then we will be closer to this short circuit impedance. Right? And if we are operating at a light load, let us say 10% load or 20% load, that times this resistance will definitely be very, very high, which will be closer to making this open circuit. So for a given resonant converter, for a given power rating of the resonant converter, by looking at this characteristic, you can also understand how with the changing load the converter will behave. Okay, so that is another advantage of doing this analysis. So another point is also we always want to know what is the voltage conversion ratio. So we are exciting this with a square wave and how much voltage gain we will get actually in this. Of course, we have the transformer to adjust, but the tank has its own property. It can actually boost the voltage or buck the voltage depending on the kind of the tank we are using. So this is basically the voltage transfer function of this resonant tank. And if we plot this characteristic, we will see that for this particular tank, if we switch exactly at the resonant frequency, then we will get unity gain. Okay. But if we drift from that, if we switch at any other frequency, the gain will reduce from unity. And of course, in this voltage characteristic or in the voltage transfer characteristic, we can also mark the ZVS and ZCS region very easily. Okay. And we can understand from this figure how by changing load or with varying load, how these voltage transfer characteristics will change. So once we understand well this very basic series resonant converter, so understanding a little advanced resonant tank topologies will not be very difficult. We can analyze in similar lines. So this is one parallel resonant converter where we have connected L and C in parallel. If we analyze this circuit in similar fashion, we will see that we'll have a ZVS region or inductive impedance region. Again on the right hand side of the resonant frequency, and depending on the load condition, the converter can behave as a inductive tank or a capacitive tank. So at light load condition, you can see this is a capacitive nature, and at heavy load condition, you can see this is a inductive nature. So if we are operating this converter below the resonant frequency, if we are switching the full bridge network at a lower frequency than the resonant frequency, then depending on the load condition of the converter, this may exhibit either ZVS or ZCS. Right? That's what this nature is saying. Now, in this topology, if we try to figure out what is the voltage gain, we'll see that previously our series resonant converter were capable of giving only maximum gain was 1 unity, but this kind of a resonant tank is actually capable of giving higher gain, higher voltage. Okay, so if it is a high voltage gain kind of application, we can actually choose to use this parallel resonant kind of converter to actually boost the voltage. So that's what it is. And again, similar to previous exercise, we can map the ZPS ZCS region in this characteristic as well. So these two are basic resonant configurations, series resonant and parallel resonant. So from there, what people have derived, which is very, very popular in many applications, and many of us have already heard this name probably, which is series LLC converter. So in IEEE, you will find lots of paper, lots of recent paper all over the world. People are doing a lot of research on this, that LLC series topology, which is basically a series resonant converter. The only thing what is done is the transformer. If you remember the powertrain, we had transformer in the main powertrain. Right? So this transformer we are assuming ideal till this point. Now we can actually use the magnetizing inductance of the transformer as a resonating element, right? So what is done here? Basically, we had that series C and L. Along with that, we have brought in a third resonating tank element, which is basically the magnetizing inductance. So we are not actually increasing the part count of the tank. We have basically three components: one capacitor, one inductor, and one transformer, which we already had. The only thing what we are doing, we are introducing some air gap in the transformer to bring in the magnetizing inductance. So previously, when there was no air gap, the magnetizing inductance was ideally can be assumed to be infinity. But anyway, it was very high, let's say in range of millihenry. Now, by introducing air gap, we can actually bring down that magnetizing inductance to our required value. So, depending on what kind of design we want, we can bring it to, let us say, 100 microhenry by adjusting the air gap. So, that will basically make this series LLC resonant. So, if we analyze this tank as before and derive the short circuit and open circuit impedance, you will end up having this kind of a character. Now, you can see that there are three resonating elements. So you have got two resonant frequencies. One is caused by our original series resonant frequency. Another one is basically the series connection of this LS and LM along with the capacitance CS. So this is another resonant frequency. So if we see that waveform of or if we see the impedance input impedance characteristic of this resonant tank, we can identify different ZVS ZCS regions, right? So for example, here if we see, we can see that depending on load condition, either this can be capacitive or inductive. So this is a region where either ZVS or ZCS can happen. Now if somebody is switching the full bridge network at a frequency higher than omega naught, will still get ZVS. And if somebody wants to achieve ZCS always independent of load, he can decide to switch the full bridge network at a frequency lower than this omega 1, the second resolution. Right? So that's what this characteristic is telling us. We can do similar exercise. We can find out what is the voltage gain of this resonant tank. So then we'll see that it actually retains that unity gain property at omega naught frequency. That is the original property of that series resonant converter. But on top of that, it gives the facility to go to higher voltage while keeping the ZVS condition, right? So depending on the load, if somebody adjusts the switching frequency of the resonant tank of the full bridge switch network, then he can actually still can operate in ZVS while achieving higher voltage gain. Okay, so this is one unique property of series LLC converter, which has made it extremely popular for different applications. So similarly, how from series resonant by introducing magnetizing inductance, we derive this topology. Similar exercise we can do to take we can take the parallel resonant converter and we can introduce the magnetizing inductance Lm. So that will make it as a parallel LLC converter. Okay. So if we again analyze this, we can again find out that it has got different ZVS and ZCS region as inferred from the input impedance character. And these two are basically the resonant frequency. One is this parallel resonance between Lm and Cp, and the other one is basically the parallel combination of Ls and Lm along with Cp. So that's the other resonant frequency. So since it is derived from parallel resonant converter, it is expected to retain that voltage gain or voltage boosting property of the parallel resonant. And that's what we can see from the voltage transfer characteristic, that it provides a higher gain, this topology. Okay, and yeah, again we can map the ZVS ZCS region in this voltage transfer. So this is basically the basic revisiting the basics of resonant converter, and also we have looked at two topologies, series LLC and parallel LLC, which are very recent topologies which people are using for different applications. Now we'll move into how this resonant converter, so having this basic knowledge of resonant converter, we'll try to see how these resonant converters are relevant for wireless EV charging. Okay. So yes, any question?
No, sir, you can proceed, sir.
Okay. Okay. So what do you understand by wireless EV charging? Basically, the right hand side picture, what it is showing that, let's say we have a vehicle which is standing on a road or any charging station. So we'll actually have to transfer the power from the ground or from the charging station or from the road plane to the vehicle, right? So there should not be any wired contact. So we can understand that the power transmitter we have to mount on the road, and the power receiver will be sitting in our vehicle. Of course, the power transmitter will be somehow connected to the grid, from where we can either take AC power and make this, which is a common approach. But again, people are talking about, since you are generating that AC power maybe from burning the fuel, so what is the point of going into recharging? So people are proposing to have charging stations which are run by solar panel. So in that case, then you might have a DC bus itself available here. So the whole system could be DC depending on the architecture chosen. but doesn't matter. So for this topic, what is important is somehow we are getting the power, and here we can have a high frequency AC. We have already seen from our resonant converter basics that we are capable of generating high frequency AC if we are given a DC signal. Okay, so that high frequency AC, if we have in that road, and we are transmitting that over this air gap, our vehicle can actually receive that power and charge its battery. So what is the principle of this power transfer? One approach is inductive power transfer. Okay? So this is very old technique, I would say, because this was first invented by Professor Nikola Tesla, when he actually had demonstrated how AC power can be transferred over air. Okay, so he had a very basic circuit which was later named as Tesla coil. So you basically have a coil which we are exciting using a AC signal or AC voltage. So we know that this coil will generate flux. Okay. Now that flux, if we place another coil which basically can receive that flux, and we connect a load resistance across that coil, then we'll see that the some portion of the flux will link this coil and will actually induce a AC voltage in this coil, which will be supplying our load. So basically, you can understand that green coil will actually place it in our vehicle, and the red coil will place the road, right? Then we'll excite this with a high frequency AC, let us say, and then we'll actually receive that signal or receive that power in our vehicle by this. Now, this is basically a transformer, right? So when we study transformer, that's essentially doing the same thing. If it is a air core transformer where we are not using any core, then this is absolutely Tesla coil, because when Professor Tesla first explained this, he tried to transfer this power over air. And if it is a core, a transformer with core, then also the power transfer is basically wireless, because there will be no wired contact between primary and secondary across a transformer. So we can apply our transformer knowledge, our basic understanding of transformer, to analyze this sort of a inductive power transfer. So from transformer knowledge, what we know that the flux, how much it is generated in the primary coil, the whole flux is not linking the secondary coil, right? So some portion of the flux is actually leaking. So that leaking flux we actually represent by this leakage inductance, right? And also we know that this, if we have a magnetic core, for this power transfer to happen, the core will actually need some magnetizing current. Okay, or even if we are using a air core kind of a transformer, to actually build the flux so that the power transfer is possible, we have to have a magnetizing inductance, right? So this is these two components. If we actually build this coil, these two components automatically come with the ideal transfer. Now, for the power transfer from road to vehicle or from primary to secondary, what is our wish list? So when maximum possible power transfer will occur, when we have zero leakage inductance, that means there will be no voltage drop. So whatever V1 I1 power we are giving from here, the whole V1 will actually appear across this branch, right? So then V1 multiplied by turns ratio will be directly V2. So no loss in voltage if we have zero leakage inductance. And we also want infinite magnetizing inductance. Why? because whatever ion is we are pumping or whatever ion is coming out of the source, we want the whole current to go to our load so that we can say V1 I1 equal to V2, right? So we don't want any current IM to actually get bypassed because of this magnetizing branch. So this is our wish list. Okay. Now let us see how it happens in the practice. So now let us say for power transfer, so give a we know that to reduce the leakage flux, it is better to use some kind of a low reluctance, provide some kind of a low reluctance path to the flux to operate. So let us say we are using some core material, let's say ferrite we are using, and we have put that coil across the ferrite material in the primary, and this side is basically our road side. And in the vehicle also, we have kept the ferrite, and we have actually connected our battery to be charged after winding the secondary across this ferrite on the vehicle side. Okay. So now,
Sir, sir, what's up, sir? Sir,
Hello, it's not audible, sir.
yes, yes, sir. That's what I'm also checking. Just to give me a minute, I'll be try to get back to sir. I'll talk to sir. Sir, Dr. Utsap, sir. So, dear participant, there was some technical issue at the subject expert end. So, you'll be joining in another couple of minutes. So, kindly stay in the meeting.
Okay, sir.
hello,
Yes, sir.
hello.
Yes, sir. We are able to hear your voice, sir. Yes, sir. Continue, sir.
Okay, okay. Thank you, thank you. I think there is a power cut in my house, so that resulted in this problem.
Sir?
Yeah.
Yes, sir.
Uh, right.
Yes, sir. You
Yeah.
can continue
Okay.
from.
So
Yes.
yeah. Okay. What people are doing to take care of this leakage inductance? So they're placing a capacitor in series with this inductance. That means we can place a capacitor in series with this AC source itself, right? So that will come in series with the leakage inductance, and we can excite at this series resonant frequency, right? So we can, from our previous knowledge, we can understand that this circuit has actually become well-known series LLC resonant tank, right? Because we have this CSLS and the magnetizing inductance LM. Now, if we excite this at series resonant frequency, as we have seen by analyzing series LLC resonant tank just a while back, that this leakage will be completely absorbed, because at that frequency this CS and LS will cancel each other. That's why this tank offers a unity voltage gain, as we are discussing when we excite it at resonance, right? So at least the voltage drop part we can take care by doing this series compensation, so that the voltage which we are applying here directly appears across the magnetizing branch, and of course the load is here, so the whole voltage can be seen by the load. Okay, now another point is, still we have this magnetizing current branch, so we are still losing in terms of current. The whole current which is coming here is still not going there, so we cannot eliminate that, of course, but we can definitely minimize the magnetizing current. Okay, so how we can do that? So if we express the magnetizing inductance in terms of this coil architecture, we will see that the number of turns and the area of the coil, and also the distance between primary and secondary, can be related by this well-known formula, right? So what is magnetizing inductance? That is basically 1 by Lm integral of the voltage which is coming across this magnetizing inductance, which is P2 basically in this case. So to minimize magnetizing current, what we can do, we can either, so we want to minimize magnetizing current, right? That means we want to increase Lm. So it's in denominator. So if we increase this, then the magnetizing current will actually reduce. So to increase Lm, what we need to do, either we can increase this core cross section, right? So that means we need a bigger coil, okay? But we can understand that for a vehicle or for any kind of a mechanical structure, the space limitation will definitely come in. So we cannot arbitrarily put a very large coil, right? So there is a space limitation on the area of this coil, definitely. So though we can have a lower magnetizing current by increasing the core cross section, we cannot go indefinite, right? So what is another option? Here we want to reduce this IM, right? So one way of reducing this IM, the integral, this integration which is happening over this time dt, right? So this is basically our switching frequency, at the frequency at which we are switching our full bridge, right? So what we can do, we can reduce this time dt over which this integration will happen. So what this essentially means, reducing this time, that we can increase the excitation frequency, right? So the excitation frequency means the switching frequency at which our switch network is operating. So that is another approach by which we can minimize this. So both these approaches are taken by designers, and they try to maximize the amount of possible power. So this is one approach. The second possible approach is basically capacitive power transfer, right? So the architecture, the system architecture remains the same. You have to have a transmitter in road and you have to have a receiver in the vehicle. But now what we are doing, we are actually placing a capacitive plate in the transmitter or in the road, and we are placing a receiver plate in the vehicle, right? So basically, when we excite this, the power transfer happens over this air gap by capacitive means, right? So if we make the architecture such that we have a current path, forward current path, which will go to the load or charge the battery, and it will come back to the source, so that the complete circuit we can get. And then if we calculate what is the effective capacitance here, we'll see that we can actually express this in terms of area of the plate and the distance between the plates, and also the epsilon naught or permittivity of the air gap, right? So this is basically the fundamental of capacitive power transfer. And interestingly, this was also first demonstrated by Professor Nikola Tesla, and this was actually done even about 6-7 years before the inductive power transfer. He had a patent on this architecture at that time. So if we try to further analyze in terms of circuits, we'll see that if we actually represent it as capacitance, we'll see that we'll have two capacitances of this value. We're representing it as 2CS, so that both of them coming in series ultimately turns out to a normal CS, and that will ease our calculation, right? So here, while we are actually exciting this voltage, this supplying the power from a sinusoidal current source, let us say given by Vn sin omega. Hello, is there a question?
No, sir. I think someone has been unmuted their mic, sir.
Okay, okay.
Sir, Mr. Wasim Babu.
Yeah, can you please mute?
Yes, I'm muted, sir. You can continue the session, sir. No issues.
Okay, okay. Okay. So when we are exciting this with a sinusoidal source, let us say Vm sin omega t, and if we try to calculate by solving this simple RC circuit, how much power will be transferred from this source to this load, we can identify that the power transfer expression, in the power transfer expression, we will have a component 1 by omega RC. Okay. So what is our wish list here? What we wish to have is the maximum power transfer from source to load in this case also, and for that we want this P naught to be Vm square by 2R. That means essentially what we are saying, this quantity, this omega RCS, we want this to be very, very large, so that we can ignore this whole factor and we can have maximum power. Okay, so that means it looks like we are saying the excitation frequency, okay, the frequency at which we want to transfer the power, we just want to have this frequency much greater than this 1 by RCS, right? From this expression, it doesn't look like it's a very tough thing to demand, okay, or it is very critical. It looks like that people should use capacitive power transfer, because here we do not have that extra magnetizing branch and no current is actually leaking out. So this apparently it looks like a easier choice to make. Okay, but we'll see what actually it is. So for that we have to take some numerical numbers to appreciate what we are saying. Okay, so for now let's forget EV charging. EV is a very high powered and big thing to charge. Let's consider a simple laptop to be charged. Okay, let's say the one I am using right now is a Dell Inspiron laptop. So what we have an adapter, right? We have an adapter. If you see the nameplate of the adapter, we'll see it's about 100 watt and 19.5 volt. That's what this adapter ratings are. So let's say we don't want that wired adapter. We want to charge this laptop battery by capacitive power transfer. Okay, so we can place our laptop on a table, let us say, and over the table we can place it very close to the transmitter because it's just we will place it on the table. So this gap between the transmitter to the battery surface or to the receiving port of the laptop, let us say, that will be only the plastic case of this laptop, right? Or width of the laptop, let us say. That is very small, 5 mm. Okay. So we are trying to power transfer, can do capacity power transfer over a very small distance. This is for EV, you can understand that this distance will be far more larger. From the road to the EV, this distance will be at least 100 times, okay, or at least 50 times, okay. And so for the laptop, we have the whole area. Let us say we decide to place our complete plate or the transmitter and receiver plates throughout the whole surface of the laptop. So we have approximately this much surface available for our Dell Inspiron laptop. Okay, and of course we can assume the permittivity of air for our calculation. So what we said in the earlier slide, we said we want the excitation frequency to be much higher than 1 by R space. Okay, and the R for 100 watt and 20 volt, let us say we're approximating the 19.5 to 20 is about 4 ohms. Okay, and given these numbers, we can calculate that the capacitance is about in hundreds of picofarad. Exactly. So by doing this, we will figure out with this calculation that to do this power transfer, we need to excite or we need to operate this system at a frequency much higher than 455 megahertz. Okay, 455 megahertz itself is a big number, and we want much higher than that. That means just to transfer 100 watt of power over a small distance of 5 mm, what we are demanding is a switching frequency. You can think of that. Ultimately, that full bridge switch network will come here, and we are demanding some gigahertz switching frequency, which is practically impossible. Even given the GAN devices which we have today, we cannot switch and transfer power at 100 watt while switching at 1 gigahertz. Okay, so this is one major issue in capacity power transfer. So what people have thought of to address this issue, like previous, where people actually had connected capacitance in series with the available leakage inductance. Here, the technique is to connect some inductance in series with our primary side plate. Okay. Then again, we'll use the same principle of cancelling this LS and CS by operating this at a resonant frequency, at this resonant frequency, so that the source sees a resistive impedance and able to do maximum power transfer, right? But it is not that simple the way I am explaining here. It looks like it has solved all the problems of capacity power transfer, but this is just the fundamental of it. And in practice, by using this sort of technique, there are products where this amount of power has actually been transferred over this much distance, and those are actually using capacity power transfer and available in market. So if people are using some Apple phones, so some Apple phones are now coming with this wireless capacitive charging, but that is even lower power. Okay, so it's about 15-20 watt of power transfer, but they are actually able to make it possible to do that capacitive transfer, and people are aggressively working on increasing this power rating and this distance so that we can actually utilize this capacitive power transfer for EV charging. Okay, so this is the basic understanding of inductive and capacitive power transfer, and this is two typical architecture what we are the whole powertrain if we talk about. So for inductive power transfer, as we can think of the whole red dotted block we can place in the roadside, and the whole green block we can actually place in the vehicle side, right? And similarly, for capacitive power transfer, with the complete circuit if we want to see, we can place the whole red dotted box again in the roadside, and the secondary plates along with the diode rectifier in the uh, vehicle, on the vehicle. Okay, and again what we'll do, given this resonant frequency, once we have designed this, we'll try to switch these networks at a at this resonant frequency. In both the cases, we have seen for both inductive power transfer and capacitive power transfer that maximum possible power transfer would occur when we are actually switching close to the or exactly at the resonance. So this could be a typical power architecture for EV charging. Okay. So once we understand these basics of resonant converter, and we also have understood how there is this resonant converter can be applied and why it is important for wireless EV charging. Next, what we will try to do, we'll see one particular problem of this resonant converter, that when we'll actually try to implement this, what kind of a problem we can face. So that is called a resonant frequency drift problem. Okay, so before moving forward, I'll try to go back to the Wi-Fi connection, because this mobile internet is going out. Whether you can hear my voice. Okay, do you continue to hear me? I am still audible. Hello?
Yes, sir. Audible, sir.
Oh, okay. I'll continue. Thank you. Okay, so to understand the frequency drift problem, we first have to understand how classically these resonant converters are actually controlled. Okay, so classically these resonant converters are controlled using variable switching frequency, which means, let us say, in this converter, when we have already decided to place this whole of the primary side power electronic circuit in the road and the whole of the secondary circuit in the vehicle, and let's say we can take some optocoupler based feedback, because for feedback also we need isolation, right? And we try to do the voltage control of this whole system, and we try to track that voltage or charge that battery at a particular voltage, or it can be current control also. Just this is just representative. So in that case, what will happen? We generate this error signal with respect to the reference and the feedback, and put it in the compensator, right? So this compensator actually generates a voltage signal when which is then fed to a voltage controlled oscillator, call it a VCO, which generates a switching frequency or a square wave of a frequency which is proportional to the voltage given to it, right? So you can understand that if the output voltage actually is drifting from the reference, accordingly the error will change and the compensator will act on the error, and that will update this voltage which is fed to the VCO, which will automatically update this switching frequency. Okay, so depending on the change in the output voltage, we can actually adjust this switching frequency so that we can regulate this converter. Okay, now the way I have drawn it, or I have shown it, so the plus sign is with the reference and the minus sign is with the feedback. So we can understand that if we take a nominal characteristic, bold black line, let us say when the position of the vehicle and the roadside transmitter is fixed, or it is initially designed such that we get this kind of a voltage transfer characteristic, then we can see that to regulate this voltage, we have to decrease Fs when the voltage error is positive, right? So positive voltage error means our output voltage has gone low, and now we have to reduce the switching frequency to achieve more gain. So in this characteristic, basically, we want to go from a lower point to higher point so that we can regulate the output. So that is the principle of variable switching frequency control. Okay. Now, this is the nominal characteristic. Once we have designed and then this is working, that's the ideal case. Now, what about this tank parameter variation, right? So, just to give perspective, so if somebody is using resonant converter for, let us say, solar PV application, and the converter is actually placed beneath the solar panel, there itself, due to temperature change, the parameters do vary, and it varies such that it creates a serious problem of resonant frequency drift, okay, for that application. Now, if we think of EV charging, definitely the converter which we are placing on the roadside, that will be here, and the vehicle, beneath the vehicle, the receiver end which is connected, that is also very much exposed to the atmosphere, right? So that is one key point because of what these parameters can vary. Another point is which people have noted, that the alignment of the transmitter and the receiver. Okay, so if we ask somebody to park the vehicle exactly on a given location so that this transmitter and receiver is absolutely aligned, then that will result in some magnetizing and leakage inductance, right? For which we have already designed and got this nominal characteristics. But if somebody has parked his car a little ahead of the transmitter, or a little away from the transmitter, then the resultant magnetizing and leakage inductance will again be different. So for this application, this EV charging application, this tank parameter variation is actually even more pronounced compared to our well-known other applications where resonant converter is used. So that means from our nominal characteristic for which we have designed the converter, the actual characteristic can shift either on the right side or in the left side. I have shown it in two separate kind of dotted lines. Okay. So in practice, this shift of the voltage transfer characteristic is very much possible. And then if we see the input admittance characteristic, then that means the IS and VT, that is the input admittance. So there also we can see that this angle between IS and VT, which is actually helping us to achieve ZVS or ZCS of the switches, which we studied an hour back. Okay, so that characteristic also will drift accordingly if these tank parameters do change. Okay, so we'll not get into this input admittance. Let us first understand this voltage characteristic. Now, what we analyze for this variable frequency control, that the automatic regulation of the voltage is possible as long as we are in the negative slope region of this characteristic, right? Because what we are doing, we are blindly, the controller, what is the controller doing? If it sees that the error is positive, it will decrease Fs, right? So that phenomena will actually regulate as long as you are either in region A or in region B, right? So if your characteristic shifts from this bold dotted line to drift below nominal, then automatically the operating region will shift from A to B and you will continue to regulate, no issues. But if your tank parameters drift such that your characteristic has become the small dotted line, then you will actually fall into the negative slope region of this characteristic, right? So now what is the problem? If we look at this characteristic on the other slope, you can understand that now for a positive error, you should increase switching frequency so that you can again be able to regulate. But this controller does not know that. It just works on the error, and it monotonically operates or regulates the switching frequency, right? So that means it will continue to drift away from its desired operating point, and ultimately the converter will basically become unstable. Okay, because this controller does not know that there is a requirement of sign reversal in this error amplifier, right? So that is the major problem of resonant frequency drift when we are trying to use this classical variable switching frequency. So there is another control approach what people have used, that is fixed switching frequency control approach, where we don't use the switching frequency to regulate output voltage. Instead, we change the excitation signal itself to regulate the output voltage. Okay, so that means what we do, we either introduce this phase modulation, right? So basically what we do, we change the effective voltage which we are actually applying by introducing this phase shift between the switches, right? So with this approach, what will happen here, we are not changing the switching frequency to regulate the voltage. So we are fixed here. Let us say the nominal characteristic when we have designed, we are basically fixed at a particular frequency. And when there is a change in load or change in input voltage, we are suitably changing the phase modulation angle so that the effective voltage we are applying gets reduced or increased. By that, we are regulating the output voltage. Okay. Now, is there a problem in this control scheme if there is a drift in tank parameter? So if we see here, if the tank parameter drifts on either right hand side or left hand side, there it is possible that there is no instability though, but there will be reduction in voltage gain because we are fixed at a switching frequency and the characteristic itself has drifted because of physical variation of the tank parameter. So there will be a significant reduction in voltage gain. Also, there could be loss of ZVS operation because the input impedance characteristic will also change, and also we can have a high circulating current. Right? So this will give very poor efficiency. So all this what is saying, though variable switching frequency control, we can end up having instability, which is a very big problem. But in this particular case, fixed switching frequency control, we can still have a good efficiency and maintain the required voltage gain by introducing something like automatic resonant frequency tracking. So this is a solution for the resonant frequency drift problem. So what has been proposed for this? That by some means, you always ensure that your switching frequency is always equal to your resonant frequency, and for voltage regulation you use this phase modulation. Okay, so this is a separate control loop which can always ensure Fs is equal to F naught even when the tank parameters are varying due to any physical or ambient condition. So this is one solution for resonant frequency. So how to implement this? So we are going towards the end of this presentation now. So how to implement automatic resonant frequency tracking, how people have done this. So in Berkeley, Professor Seth Sanders had proposed this. If I remember correct, this was first done for capacity power transfer only. So what he proposed to do is using phase locked loop based automatic resonant frequency tracking scheme. So he applied this to the series resonant converter, right? So here, basically, the point to note is when in this converter we are exactly switching at resonant frequency, then this current Is and Vt voltage, they will be in phase. Okay. So by exploiting this nature, what this group has suggested that you can do a zero crossing detection of this current and basically generate the gate pulses from that zero crossing detected signal, right? So essentially what will happen that always the voltage Vt will actually be in phase with this current Is. By that, you will ensure that your switching frequency is exactly equal to the resonant. So that was the kind of a proposal. So, but this has a limitation. So, one limitation is very apparent that when first the circuit will be starting up, right? During that startup condition, you do not have any current because the circuit is first starting up. So, the output of the ZCD, you will not get anything. You basically get some noise here, right? So, then you need to have some additional startup circuit so that your circuit can start up at some frequency and then this phase lock loop can start operating. Okay, so this is one problem in this approach. Also, let us say the implementation of zero crossing detection is not very trivial So there will be noise problem if somebody wants to actually implement it. And the third thing is, this is particularly proposed by looking at this characteristic, that this IS and VT has to be in phase for this converter, right? So, but this is not a generalized solution. For any resonant converter, this cannot be applied, because there are topologies where IS and VT does not remain in phase when we are switching exactly at the resonant. So this is not a generic solution. Another approach which is quite popular, I think some products also have been built using this approach. So this was done by the group in Virginia Tech by Professor Fred C. Lee. So this is a similar approach to the phase lock loop. This is basically called a pulse width lock loop. So I'll not go in the details of this. We can refer to this paper if you want to understand more. So here basically the pulse width of this secondary side gate of this MOSFET and this primary side MOSFET, that has been equalized. Okay, and it has been observed that when these two MOSFET gate pulses are actually equal, that time you can have a tuned operation. Right? If you can ensure that gate pulse of this and this is same, then you can automatically ensure that the switching frequency is at resonance. Okay, so this is a series LLC converter, you can see, which we studied some time back. On series LLC converter, this technique has been applied. So this also has some serious problems, which has been solved by introducing some other circuit in different papers. That sensing of any VDS or drain to source voltage of a MOSFET is always tricky. So when we work in hardware, we know the MOSFET VDS is a very noisy signal. So we had to use some sophisticated circuit to cleanly sense this VDS. Okay. And the algorithm itself has some problem. It has been implemented in digital. So the accuracy of the system actually will depend on how precisely we are able to calculate the difference in pulse width. Okay, so we have to calculate the difference in pulse width between M2 and M3, let us say. So in that case, your digital processor resolution has to be very high. And again, this phenomena, that when Fs is equal to F naught will happen, that time we'll actually see the pulse width of M2 and M3 be equal. That phenomena is specific to series LLC time. Again, it cannot be generalized for any resonant converter. So we understand that the resonant frequency drift problem has some solution, which is automatic resonant frequency tracking. Two of the methods we saw in literature, there are many more methods, but all these methods have some limitation, and the common limitation is it's not a generalized approach which can be applied to any resonant converter. Okay, so with this motivation, what I worked during my PhD at IIT Kanpur. So I tried to develop this phase relationship based ARFT. So couple of techniques I developed. The main motivation was to have this implemented in general resonant converters, right? So the technique should be such that it can be applied to any resonant converter. So I'll not get into the mathematics because we have the short time. We don't have much time left now. So the basic idea or the basic principle of this was to use some means to extract a phase relationship in the in this resonant tank, right? So what we can do, we can look at a couple of variables. Let's say I look at the inductor current and some capacitor voltage and try to figure out that what is the phase relationship between that two variables when we have exactly tuned condition, right? And we can also see, let us say here I have shown phase relationship of a variable pair, and here we can see that the variable pair will be in quadrature, or the one variable will lag the other variable by 90 degree when we are exactly at resonant frequency, right? But when we drift from that resonant frequency, that time it will, in one case, it will start lagging more than 90 degree. In another case, it will start lagging less than 90 degree, right? So by looking at this, we can actually form a loop, right? So we already know what should be our phase reference. We can dictate that the phase between these two variables, we want to keep always at minus 90 degree, right? So that is our phase reference. And this phase relationship we can actually extract from this plant by sensing some variables, and then we can form a loop based on the phase error. Okay, we will have a compensator, and that compensator will actually generate a correction term which will be added or subtracted on top of a nominal voltage, right? So that nominal voltage or plus minus the correction term will give us a input voltage to the voltage controlled oscillator. Now, depending on the variation in the phase, whether it is lagging more than 90 or less than 90, we will adjust the switching frequency automatically in this loop. Okay. By that, we will always ensure that this phi star is equal to phi in closed loop, which will automatically ensure that Fs equal to F naught in closed loop. So that is the general proposal or general idea of this technique. So there is some exercise now. One obvious question that for a given arbitrary tank network, how will you decide which variable pair to choose? On which variable pair will actually operate to achieve this resonant frequency track, right? So that's a general question which I tried to address in the thesis. So for that, I actually developed one method. Okay, so that method actually decides how to choose the variable pair. So let us say we have decided the variable pair, and then we have to design this controller, right? So for that, we took a ramp variation approach in the resonant frequency, because we can understand that the tank parameter variation, or this as we are talking about the placement of the vehicle over the road, whether it is aligned fully or not. So these sort of phenomena are very slow phenomena, right? So even if it is varying due to temperature or by the position of the vehicle, so this is a mechanical activity. So compared to the switching frequency, that variation in resonant frequency will be very slow. So we assume that the resonant frequency will vary with time on a very slow fashion, and our switching frequency has to ultimately track that resonant frequency. So that was the idea of this plant modeling, right? Plant modeling and controller. So what we actually did, we ensured for a given ramp variation in resonant frequency, we ensured that the steady state error is minimum. Okay, so based on that, we decided the controller, the integrator basically, KIYS. the integral constant we decided based on that. Also did extensive work on how to decide the variable pair. I'll not explain that here because there's quite some involved mathematics. But what I can say, once we developed this generalized method, we applied it to parallel LLC and series LLC both, and we actually had decided the variable pair to be used for both parallel LLC and series LLC tank by using the proposed method. Okay, so once we have done that, rather instead of going into this, what will be a little more interesting to people, I can show a few results or the technique how the hardware was developed and experiment was done. So this is one parallel LLC converter what used in lab, and this is the analog controller which we are talking about. So the ramp variation in resonant frequency, to create that in lab, what we did, we made a variable inductor kind of architecture which we can move the core in and out of this winding. So that will create a variable inductance, right? Which will ultimately vary the uh, resonant frequency, right? So these are some steady state results. So between open loop and closed loop, by measuring the frequency, we can see that the desired 200 kilohertz of resonant frequency is actually tracked in closed loop, where we achieve 200.5 kilohertz. This is very good accuracy. And also, these are a few more steady state results at different resonant frequency. But this is something interesting what we are able to achieve in lab. Once we moved that inductance, in the coil, the variable inductor, when we moved, we were actually able to create this variation in resonant frequency, and we measured how the variation in switching frequency is. So we were able to see that the steady state error in the ramp variation obtained from the experiment was actually very close to the design what we made. So this was kind of a demonstration for this resonant frequency drift problem and its solution. Okay, so I had quite a few results which yeah, I think we actually experimented for step change in resonant frequency also by doing some mechanism, right? So if we connect two inductors in series and use a switch across one inductor, and when the converter is running, you actually turn on the switch, right? So that will create a step change in resonant frequency. You can understand. Because the effective L value has suddenly changed. So we saw that the proposed controller actually able to track it and reach to the track the new resonant frequency, even when we are giving a kind of a step change. Yeah, so yeah, we tried the step change in capacitor also to see whether the controller is working, and we saw good performance there. So just to conclude this presentation, so what we learned, we saw the basic features of resonant converter. Then we saw how the soft switching principles are, the basics of soft switching, how it happens. Then we saw series type of resonant converter. Two series type of converters we saw. One is basic series resonant converter, one is series LLC resonant converter. And we saw that they can give load independent unity gain. And parallel resonant converter and parallel LLC resonant converter, they can provide load dependent high gain. So this also we saw, right? Then we move to application of resonant converter in wireless EV charging, where we saw inductive power transfer and capacitive power transfer approaches. And from this experience of understanding resonant converter, we saw that the inductive power transfer can be modeled as a basic operation of series LLC resonant converter, and capacitive power transfer can be modeled as a series resonant converter. Right? So this was the basic understanding in the first half of the seminar. And then we saw what is the resonant frequency problem in resonant converters, how it causes instability in classical variable frequency. And also we saw if somebody used phase shift control at a fixed switching frequency, how there can be loss of gain and efficiency, right? So this also we saw. And then we saw a couple of methods for automatic resonant frequency tracking. And also we saw a generic approach which can be applicable to any resonant converter. Okay. So, and we saw some experimental result where if we estimate numerically, you will see that the proposed phase relationship based ARFT method actually achieves less than 1% error in frequency. These are some of the references of what I did not talk in detail is basically the implementation or the analog circuit what I had developed. So if you are interested, you can refer to these two papers where all details about phase relationship based ARFT technique has been explained. Okay. Thank you. I'd like to take questions if you have.
Okay. So now it is over to the participants. It is time for us to have the interaction. And if you're having any doubts, clarification to be get clarified in the subject, so you are most welcome. You can post your question in chat box. Dear participants, if you are having any doubts or any clarification, you can post your question in the chat box.
Thank you.
A few people has been given no questions, sir. Thank you. Okay.
Yeah, thank you all for attending this session and thank you for inviting me for this talk.
Sir, fine. Sir, actually, I'm having a small final things from my end, sir. I'm having small clarification, sir. Actually, in your presentation, you are given inductive power transfer as well as capacitive power transfer, sir. Capacitive power transfer. And you said that before inductive power transfer takes place, the capacitive power transfer has been came literally earlier. In as of now, still why it is not getting firmized? Why? Because since we are still we are going for charging in physical mode only. Why the wireless power transfer is not getting popularized as of why it is not getting commercialized as we expected, sir, right now?
Okay. So to answer this question, so we can see efficiency is a big problem in
Yes,
let's.
yes. Mm-hmm.
So we from this discussion we can understand that when we are talking about EV charging, so that means the battery you have to charge in kilowatt range, right? It's not a
Yes.
50-60 watt power range. So at that power level and over the distance from the road to the vehicle, if you have to transfer the power, as we are seeing in this slide, right? Even if you do resonance and cancel this leakage inductance part, this magnetizing inductance will actually cause you to reduce the efficiency. So that is a major problem in inductive power. Okay.
Okay. Mm-hmm.
That's why it is people are working. So people are trying to improve this. I hope it will be commercialized. and I think it will be definitely commercialized in near future. There are a lot of research across the world going on. And for capacity power transfer, till my knowledge, I mean, best of my knowledge, the attempts for capacity power transfer high power level is actually less, okay, compared to inductive power transfer. Only in Cornell University, Professor Khurram Afridi, he is doing some research on this, and from his research, what uh, till the point which I have studied actually, but I figured out that capacity power transfer, there is a big issue of this voltage VC. You know, when you are trying to transfer a higher amount of power, this voltage VC will increase. Okay, so you can understand physically this voltage is coming in the air gap, right? Beneath the
Yes.
car. Okay, so there is a very big risk hazard in this capacity power transfer, because you will be able to transfer good amount of power if you are operating at a high frequency, but the voltage across this air gap will be unrealistically high. So you have to take care of that. That is one limitation in capacity power transfer, which is stopping it for easy commercialization.
Okay, sir. Okay. Okay. Thank you, sir. I got clarified. Sir. So, any more person willing to ask your queries? You are most welcome. I think there was no any questions. So, if you don't mind, sir, I want to. Can you turn on your camera, sir, for a while, so we can take some
Yeah,
screenshots, sir.
sure, sure.
Participants, I am requesting, if you don't mind, can you turn on your camera for a while, so we can take the screenshot. Okay, sir. Thank you, sir. Thank you everyone for honoring
And
that. So now it is a time for me to propose a vote of thanks. So very happy to see that you are detailed, full of knowledge on power electronics. Actually, I noted some of the few points of this presentation. You have given very good conclusion, summarizing the things which has been taken by use of the last almost 2 hours. You have been given a basic operation of switching, operation of normal switching, hard switching, and as well as soft switching, and given about the resonance converter application, as well as series type, parallel type, and completely how it is going to happen wireless, where you have been given very good explanation, sir. So definitely our participant also got a very good insight knowledge about this resonant converter and what other things are happening in that research area. Also you given your outline, sir. Definitely it may be a good session which we came across this FDP, sir. And on behalf of complete team of NS Technical Service Center, we are conveying our sincere thanks and appreciation for you, sir, for giving your valuable time with us. And thank you, sir.
thank you. Thank you for inviting me. And it was a nice session. I think we had a lot of audience, more than 40-45 people I saw. Okay.
Yes,
So
sir.
this, I believe, is a nice session. Thank you for organizing.
Yes, sir. Thank you, sir. Thank you, sir. Thank you for your support, sir.
Okay. 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 So
Yes,
I'll drop off.
yes, sir. One more thing, sir. If you don't mind, can you share
Yeah.
the presentation to us, sir, so that we can share it with the participant also, sir?
Okay. So this presentation is actually still evolving.
Okay.
So, and I actually present it at in many places. So you have the video recording, right?
Yes,
You
the
have
video recording we are
recorded
going
this
to.
video.
Yes,
Yeah.
video has
So,
been recorded.
so I would recommend that please share the video with the participants so that they can go with the presentation along with my voice. That will
Okay.
be easy to understand. But yeah,
Okay.
so the presentation itself may not be that useful.
Okay, sir. Okay, sir. Okay.
Okay. Thank you.
Okay. Thank you, sir. Thank you.
Okay. Okay.
So, dear participant, actually, we have been posted the feedback link in the chat box. Kindly have a look into the chat box, and we have been requested to give the feedback before the leaving the session for the day. Thank you for your support extended throughout the day as well as throughout these 3 days of FDP program. And tomorrow, and just I want to remind you that tomorrow we are having a packed session on FDP on this retrofitting and the commercial. What are the things will be required for retrofitting the existing vehicle into electric vehicle? We are going to have the session on morning, and followed by we are having a session on EV charging and other aspects we are having. And afternoon session we are going to have one industrial experts who is going to explain about the battery management system. So it is one of the session where the industrial people are going to take. So I'm requesting tomorrow session. Kindly ensure that you have been attending the session and give your support for us, please. And any issues in opening the feedback? It is opening.
Yes, sir. Opening, sir.
Okay, sir. Thank you, sir. Thank you for confirming. And tomorrow we have been successfully completed 3 days of this FDP program. Once again, I posted the feedback link as requested by Ashna Joseph.